let's quickly go into it. So this is the second function we have over here. This over here is the function, and f of x is given by k into bracket 1 plus 2x, and it is valid for the values of x being greater than 0 and then less than or equal to 2. It is 0 elsewhere. So our task is first of all to verify that f of x satisfies the condition of PDF. And the condition is that it should give the function a value which is what? Greater than 0. Right? Or it should be non-negative. Then the second one will be determining the value of x. Now, after solving all this, this is a visual representation of the function we would be working on. Alright, so this is just a visual one where we know our limits are from what? 0. So our limits are from 0 to what? 2. This is the function. So it's actually a very, very linear function. Now let's quickly go into it. So we know our given function, f of x, so we are verifying for non-negativity first of all. So for this function, which is f of x, is equal to k into bracket 1 plus 2x. Now take note that if you take only this one without the k, that is 1 plus 2x, it would always be greater than 0 if x is what? Greater than 0. Let's try that and see. So we are working it for this range. So if you put x to be 0 there, all this gives us what? A 0. So 0 plus 1. This alone is what? 1. Alright. So we can say that if f of x values are all going to give us values that are greater than what? 0 for every x that is greater than or equal to 0, then it should imply that our f of x is actually what? Going to be greater than 0. If now the condition is on our k here. So if k is greater than 0, because at the end of the day, if you have the one in your bracket, only this one giving you a value that is greater than 0, and this one k over here is going to bring it back to negative, then you have your f of x being what? Negative. You see? So if we want this to give us a value that is greater than 0, then as we have verified that for this range of values, the bracket would definitely give us a value that is greater than 0, then our k, the k we want here, will now be what? Must be greater than 0 so that the function would hold for non-negativity. I hope that is clear. So let's go to the second one, that is solving for the value of k. So to solve for our value of k, we first need to apply the normalization condition, right? So that is it over here, which says our integral from negative infinity to positive infinity should be what? Equal to 1. That is, the area under the curve should be what? Equal to 1. But we should note that our f of x is equal to 0 for any other values apart from less than 2 and then greater than 0. So we are not going to use this infinities, but then we are just going to use our integral of k into bracket 1 plus 2x dx for lower limit 0, upper limit 2 equals 1. You see? Then now we would have to what? Input our integral. So to solve this integration, we would need to what? Expand it. Now we know that this one, this k over here can come outside, so that it now becomes k. Then we now have our integral from 1 plus 2x dx, right? With our limits 0 to 2. All we are doing is we are moving this k outside. You see? Then now, since there's a plus here, when it comes to addition and then subtraction of integrals, we can expand them linearly. So this over here also gives us our k in one bracket, then into bracket we have the integral of 1, that is this first term here, dx. So an integral of 1, and then it also takes the values from 0 to 2, plus the integral of 2x, that is this second value here, dx, with our limits from 0 to 2. You see? So now this is what we want to solve for. This is what we want to solve for. So for this very first one here, take note of this k, because after solving everything in this bracket, we'll come back to the k. For the first one, which is the integral of dx, or integral of 1 with this limit, the integration of a constant 1 would definitely be what? X. So it is this x that we apply our limits on, and that is going to give us what? A 2 minus 0, which is equal to what? 2. Then we come to the second one, which is the integral of 2x dx with our limits. If we integrate 2, or we can also choose, since 2 is a constant, we can bring the 2 out. So I have 2 with our integration on just x dx, right? So applying our integral rule, this is then going to give us our 2 outside, right? And if we integrate x, we are going to get x squared. So x squared over 2. You remember, you just increase the exponent and then you divide the whole term by that exponent with our limits from 0 to 2, right? So we now solve for this limit over here, and that should give us what? Our 2 then into bracket. You know, if we put the value of 0, we are still going to get 0, so we should just focus on the value being 2. So we have 2 squared all over 2, right? And that now gives us, 2 times 2 squared gives us 4, then 4 over 2. We can simply cancel these 2's out, and then we are left with what? 4. So for this integration we had over here, that is this one, we had a value of what? 2, and then this also gave us a value of 4. So we now substitute it back into this one to get the answer for our integration, right? So let's move to the next page and then do that. So solving now for this by doing our substitution, we had what? 2 plus 4, and that gives us what? An answer of 6. But let's take note that from here there was a k that was introduced. We introduced a k, this here. So that k now needs to come back here. So all that we've done implies that if we are to bring our k to this integral from 0 to 2, which is equal to, only the integration part gave us 6, right? So we bring our k over here, so 6k or k6, right? Then how do we get our k? We remember that we said we are applying this word normalization here, right? Which means the area under the curve should give us 1. So then we come back here and say that it implies that our k times 6 should be equal to 1. Then we now make our k the subject. How do we do that? We have to divide both sides by 6, and we know this cancels this, and we left our k being equal to what? 1 over 6. You see? So this is our k we want, and hence that question has been solved, right? So what have we done? We've been able to determine, or we've been able to solve to show that our function is actually a what? Probability density function, because any value of x, especially for that which are greater than or equal to 0, put inside our function gives us f of x being greater than 0. And then secondly, we have been able to solve for the value of k. See you in our next video.